Laurent phenomenon.
Today's speaker at our seminar is Professor Retakh, who will speak about the non-commutative Laurent phenomenon.
Okay, so thank you. Okay, so that's the title. Okay, and so first let me recall what are Laurent polynomials. So if you have variables, well, commutative or non-commutative x1, xn, then you consider polynomials in variables or inverses with a given coefficients, and so they are called Laurent polynomials. Okay, and so now let me explain what is Laurent phenomenon. So Laurent phenomenon. So suppose you have variables x, y, z, and then you consider just, you apply Laurent polynomials to these variables. So you have this f, y, z, so those are Laurent polynomials, say f2. N, x, y, z. So you call those, so then you have new variables. And then you iterate this procedure. Sorry, this must be 1 here, 1 comma, and z1 bracket. This is x2. I'm sorry, that must be x1, yes, y1, z1, x1, y1, z2. Then we continue. And then you ask, so the questions are, so all the iterations, so Laurent polynomials, in the initial variables, x, y, z. Well, it's rather rare, so let me consider just a couple examples. So the first example is just a stupid example. So for example, you have two variables, x, y, and then you go, say, to a new variables, which is y inverse, well, okay, so y inverse x plus y. So those are just, well, Laurent polynomials. Then you go to x plus y inverse, and here you have x plus y. And so you stuck, because so this guy is definitely not a Laurent polynomial. So this is the first example, which is negative. So a positive example is the following. So let's consider the following. So the sequence of y's, which given, say, given by the following which are connected by the following formulas. So k is just an integer. So rk is also an integer. And we assume that k is equal, say, to r1 if k is odd, and r2 k is even. So you just have to do this. And so then you may have this, so then you just may consider, so this is sequences y1, y2, y2, y3, which is defined by this equation. Then you consider y3 and y4, which is also defined by this. So on. And actually, so that's, this is, and so, and then, so you have, so this is, and so you have the Laurent phenomenon, and it follows, and again this is in the so here variables are commutative, and it follows from the theory of cluster algebras by Vladimir and
Does it also follow from your results?
yes, in the non-commutative case, yes.
Ah. So you can
But
make,
in the commutative case, it just it was.
but in particular, you can derive it from
Yes,
your results.
yes. So yes. So we can derive this independently of this theory.
And it may be easier your way.
It's easier. It's easier. Yes, it's easier.
Nice.
It's easier. On the other hand, so this is so we did this such things in the non-commutative case as an introduction to non-commutative cluster algebra. So this the initial.
So this example, but can everything that they do be derived from your theory or only some of it?
Well, for such sequences, yes. But
they have other
but they have there are other examples.
So not all the stuff can be derived from you.
Not from what I'm going to tell today, but we are preparing just a paper on non-commutative cluster algebra. So hopefully.
So possibly and hopefully all this commutative will be a special case of
yes.
corollary.
Yes, or at least part of it.
Yeah.
Part of it. So, all right. Okay. Now then, so that's the first part. Now let's go to the non-commutative part. So non-commutative part. And so first, so non-commutative Laurent phenomenon. Non-commutative Laurent phenomenon. So example discussed by Kontsevich. And this is the paper's archive. So he actually, so their explanation, one he is interested in it, it's related to his theory of non-commutative integral, well, some non-commutative integrable systems. So I will mention just one interesting invariant connected with this. But so Kontsevich formulated just a very simple question. So the conjecture was that, for example, that you have suppose you have x, y are just three non-commutative variables. Then define just a Kontsevich transformation of this vector, and this can be written as x, y, x inverse, and 1 plus inverse. And so the conjecture says that if you define xk, yk just as a sequence of Kontsevich transformations, so here just k times, then xk and yk are Laurent phenomenon. Laurent polynomials in x and y. Now, since this is an experimental mathematics, so can I write here or better not? So then the way to check, so that's the computer check, is just this in the following. So you assume that X is just 2 by 2 matrix over with integers, and you assume that the determinant of this matrix is 1. Then X inverse is, like as we know, is D minus CA. Well, you can do the same for Y. And and to check that, to take actually any matrix for x, any matrix for y, and to do this, all these transformations. And if you are getting actually matrices with integer coefficients, then it gives you a hope that the Laurent phenomenon is here. So this is what Kontsevich explained. All right, now the history. So that's the history of this conjecture is the following. So that the first, it was proved by Alexander Usnich. And so a student of Kontsevich for just so in this case, I believe it was 8. Then just Diffrancesca and Cadam. Basically 2 math physicists. In the case when R1, R2 just pairs, 2, 2, or 1, and 1, 4. And it was done in 9. They had an advantage that they just, they showed that in this case, xk and yk Laurent polynomial, but also with positive coefficients, which is important. So they used actually their theory of non-commutative integrability. So just approached by physics. Then Usnich showed for any R, for 1 R1, R2, the proof is 2010. But actually, so his proof is non-constructive, and he used actually very heavy machinery from algebraic geometry, derived categories, and so on and so on and so on. Okay, now
That's not really a proof.
Well, I didn't know. Then in Arkady Berenstein and me proved for actually any R1 and R2. And this is just 2010, and that's again 2010. The proof is actually, as you will see, is quite elementary. But then it was an interesting development, and then Lee and Schiffer and this is 2011, they proved that just xk and yk are polynomials, Laurent polynomials with a non-negative coefficient.
And they also prove positivity.
Yes, they prove positivity.
And the proof
for it's rather elementary, but it's combinatorics used D chords and so on. This is for R equals R2. And then a student so a graduate student by Berenstein generalized this for any R1.
So now the positivity is also non-proof.
Sorry?
The positivity conjecture is also proof.
Yes, and the positivity conjecture proved here in this case and here in that case.
And it's a different method, not your method.
It's completely different. It's different methods. So the method that I'm going to discuss are very primitive, as you will see.
Yeah, but they are more complicated probably because you only have to.
They are more complicated. So basically, I'm talking about non-commutative high school algebra. Right, so that's this one.
What if you have other expressions, you have R1, R2, R3, for example?
No, R1, R2, R3,
Not true?
it is not true, I believe, in the commutative case.
I don't know.
There is a version of this phenomenon formulated by Kontsevich, when we have more variables and so on. This follows from our general theory, but it is not published again. So I'm talking about this. So let me just return back to this. Okay, and so first of all, so again, so we have just this sequence. So x1, which is xy minus 1. xk plus 1 equals xk yk xk inverse, and yk plus 1 is equal to xk, sorry, it's 1 plus x k rk. Okay, and this is xk. Oh, it's 1, so I'm correct. Yes, I think it's correct. Oh, sorry, it was of course. So you have this. And so first of all, that there is actually invariant. So note that, so proposition that the expression z, which can be written in this way, this is just actually anti-commutator. So this is just a commutator. Of xk and yk. And this is invariant. And this is actually one of the reasons Kontsevich just was interested in this sequence. Let me provide a proof to see that all proofs here are actually essentially trivial. So you have xk plus 1, yk plus 1, xk plus 1 inverse, yk plus 1 inverse. Okay, so let's use our definition. We have xk, yk, xk minus 1. For this you have 1 plus yk, xk minus 1. Next you have this, so this thing invertible, so you have xk, yk inverse, xk minus 1. And then you have, so this stuff invertible, so you have xk, 1 plus k minus 1, and then you have xk. Yeah, that's okay. So you have this. And now you can actually cancel so these two guys. Then here you have just one variable, k, so you can actually cancel this, and the result is exactly xk, yk, xk inverse, and yk inverse. And that's the. Well, but actually, all people who worked with this, so they understand this. So physicists actually even call this Z was called conserved quantity. Okay, now let me discuss just other properties. Well, the first is actually trivial, and it follows exactly from the definition that you have just z, yk. So this follows exactly from the definition. 2 is that says that you have just this. So that's actually easy to see, because so this is the left-hand side can be written as so I will leave it. So this is I will leave. So I will leave this. And so this is because actually this is actually what's this? This is actually so this is xk, I think. So it's easy to see. And 3, and so 3 is more interesting, and 3 says that this. So I will probably skip this, but it's interesting. I would like actually
So
to...
this, how did you come up with this? Did you first get them with the matrices?
No. This is
natural.
Maxim works with the matrices.
So that was natural.
No, it was natural. So you tweak a little bit this. No, but and so let me just make a comment. So first of all, about 2, you remember this the commutative analog. So commutative analog for when z equals 1. This is exactly what appears in the in the Laurent phenomenon by
Oh, so that's the motivation.
Yeah, so that's the motivation, but it's very interesting that z is here, and I will write in a couple of minutes formulas when yk minus 1 is in front. Now, what is interesting is 3. Now, 3 is that actually people doing, quantum algebra will write this as Q but Q is just belong to a field, to a scalar. And here, this is also sort of a quantum expression, but Z is non-commutative, and you input Z inside. Also, are there any questions?
And it's natural to put Z in the middle, not on the left hand.
It's natural when you are writing formulas, then this is...
No, I said that.
Well, sort of. Okay, now let me just reformulate the project. So reformulate. So rule number 1, so forget all x's. Because if you know z, you can express any x's. But, so this identity shows that you may define z actually without x's. So let's work with variables